to be talking about identifying using complex numbers. This is day 2. So now we're solving the equations, okay? So what we're going to do, let's solve this. Let's add the 9. So we have x squared equals -6, okay? And before, we weren't able to solve something like this because we have a negative in front of it. But now, since we have imaginary numbers, we can solve this. So we can square root both sides, do plus or minus. So x will equal plus or minus I square roots of 6. So we can rewrite it in value of I. There we go. So let's do another one. Let's subtract the 7. So x squared is equal to a -54. Square root both sides. So x will equal plus or minus I square roots of 54, but we still have to simplify the square root of 54. Well, the square root of 54 is 9 times 6. So x will equal plus or minus 3i square roots of 6. And now we've got there. All right, finding the zeros of the function is just the same. Now we have the p of x equals x squared plus 98, but this time we're going to plug in 0 for the p of x, and now we're going to solve. Oops. Now we're going to subtract the 98. So we have a -98 equals x squared, square root both sides. So we have x equals plus or minus I square roots of 98, but we have to simplify the square root of 98. So x will equal plus or minus I square roots of 49 times 2. So x will equal plus or minus 7i square roots of 2. Okay, same for down here. I've added a fraction. So if 0 equals -1/5 x squared minus 10, I'm going to add the 10. And I'm going to multiply by a -5. So we have a -50 equals x squared, square root both sides. So we have x equals plus or minus I square roots of 50. Simplify that 50, which gives us 5i square roots of 2. So we're just combining our knowledge of the value of I and are simplifying our radicals. Next up is a chart that you're going to see, and we can actually find different values of I to a certain power. What we're going to start off is I is equal to I. Next, I squared is -1, and we're always going to be in terms of I or -1. Now, I cubed can be rewritten as I squared times I, because we know what those two values are. And those two values are -1 times I, which gives us a -I. We're going to do the same thing for I to the 4th, which is I squared times I squared, which is a -1 times a -1, and that gives us a 1. Okay, we're going to do that same for I to the 5th. We can split I to the 5th up by I squared times I to the 3rd. I squared is -1. I to the 3rd is -I. So that is going to be an I. I to the 6, we can do I cubed times, oops, let's do I squared. Let's do I squared instead. I squared times I to the 4th. Well, I squared is -1, and I to the 4th is 1. So that's going to give us a -1. Next is I to the 7th. Let's do I cubed times I to the 4th. I cubed is -I to the 4th is 1. So that's going to give us a I. I to the 8th is I to the 4th times I to the 4th, which is a negative, or sorry, which is a 1 times 1, which gives us a 1. And if you notice, there's a pattern that repeats. It goes I, -1, -I, 1. I, -1, -I, 1. And it keeps on repeating just with these 4 values. So we can use these to solve different expressions or simplify different expressions with larger powers. Okay, so we're going to use that. So if we do number 1, we're still going to distribute. So we have 10I cubed minus 24I to the 4th. Okay, so what we're going to do now is we're going to replace I cubed and I to the 4th. Well, I cubed is -I, and I to the 4th is 1. So this is -I, and this is 1. We replace it, and so now we get -10I minus 24. Well, we have to make sure that this is in standard form. So this is going to be a -24 minus 10I. All right, let's do our next one. Make sure we distribute that negative at the very end. So we have 8 minus 2I to the 4th plus 3 minus 7I to the 8th minus 4 minus I to the 9. Okay, and let's look back. I to the 4th is 1, I to the 8th is 1, and I to the 9th, if we keep on going back, is just I. So let's fill these in. So we're going to have 8 minus 2 plus 3 minus 7 minus 4 minus I. So now let's simplify. 8 minus 2 is 6. 6 plus 3 is 9. 9 minus 7 is 2. 2 minus 4 is a -2 minus I. And we have our final answer.